Hey everybody, hope you're doing well whenever you are. Um, we're here for day 19, 2015 for Advent of Code. This one's going to be an interesting one because I've actually already been working on it for an hour. So I'll still go through I'll catch you all up. I'll go through read through the statement, through the problem, I guess. And then I've already solved part one, and I was about, I don't know, a half an hour, 45 minutes into part two. So I'll try and catch you up when I get to part two. So the issue that happened was I had to stop in the middle of my previous recording, and so I paused in OBS and then went and did some work and came back, and my computer had crashed. And so I can't seem to get the recording to work. I don't know if I'm just using the wrong recording. I mean, I'm using OBS, but maybe I'm recording it in a way that I can't like get the part that wasn't broken out of the video. Anyway, it seemed easier to me to just start over and do it. So that's the plan. We're going to I'll just catch you up to where we're at. So with that, we will read the problem statement. So this one is medicine for Rudolph. It says Rudolph the red-nosed reindeer is sick. His nose isn't shining very brightly and he needs medicine. Red-nosed reindeer biology isn't similar to regular reindeer biology. Rudolph is going to need custom-made medicine. Unfortunately, red-nosed reindeer chemistry isn't similar to regular reindeer chemistry, either. The North Pole is equipped with a red-nosed reindeer nuclear fusion fission plant, capable of constructing any red-nosed reindeer molecule you need. It works by starting with some input molecule and then doing a series of replacements, one per step, until it has the right molecule. However, the machine has to be calibrated before it can be used. Calibration involves determining the number of molecules that can be generated in one step from a given starting point. For example, imagine a simpler machine that supports only the following replacements: H to HO, H to OH, and O to HH. Given the replacements above, starting with HOH, the following molecules could be generated. And then it gives you a list. And the way to think about this is basically you can just try this replacement for both the H's. You can try this replacement for both the H's. And then you can try this replacement for the O. And that gives you all of these. So there's 5 of them, but only 4 are distinct, is what this is saying right here. And then it says Santa's favorite molecule, ho ho ho, can become 7 distinct molecules over 9 replacements. So with ho ho ho, you can do 9 total replacements, but only 7 of them are unique. The machine replaces without regard for the surrounding characters. For example, given the string H to O, the transition H to OO would result in OO to O. Now that might be like a hint to solving part 2. Anyway, we'll come back to that. Your puzzle input describes all of the possible replacements, and at the bottom, the medicine molecules for which you need to calibrate the machine. How many distinct molecules can be created after all the different ways you can do one replacement on the medicine molecule? Well, you can see I've already solved the first part. So this is the input you're given. I'll remove this. So here's all the replacements, right? There's like 40 or so of them. And then here's the molecule. And this one is mine. This is the one I'm given. Yours might be different, but I presume it's largely the same in that you have a bunch of replacements and then some things. So for anyway, there's the problem statement. So for part 1, the question that, or what seemed easiest to do was to just say, okay, why can't I just go through this list and see if I can replace, and then go through this string and see how many times I can replace it and then just keep track of it. The one gotcha is I have to keep track of the replacement itself so that I can, make sure I only keep a unique list. And when you're thinking about a unique set, hash sets are what come to mind. So my solution looks like this for part 1. You can see part 2 is running. We'll get to that in a second. But for part 1, I got 509. And basically what I'm doing is I say, okay, well, let's call split once on the NN, and that will give us the replacement in the molecule. And then for the replacements, I just need to go through the lines and call a split once on them, and that will give me a vec of 2 strings for the replacements. So then I just go through each of the replacements, and I had to look up these functions because I hadn't used them before. So I kind of Googled around in the previous video looking for some string manipulation, because it felt like using string manipulation might be an interesting way to do it. I'm sure there's other ways to do this. And in fact, if you have another way, that I'd love to see it. But the idea was basically I go through each of the replacements, and then I find all of the places where that replacement is. And then and so there might be more than one, right? The way to think about this is there might be more than one place I can do a replacement. And so then I do that replacement, which is this part right here. I use replace range for each of the indices. And then I insert this into this hash set. So now I've gone through all of the replacements and all the places that it can be found in the string. And then now I just, the length of the hash set is how many times, which is 509, right? So that one wasn't too tough. That feels like, because the list is small and you're basically just doing a scan of this for each of these 40 some odd ones, like maybe each of them return 5, the sample set is relatively small. And that was part 1. So so that brings us to part 2. And I'll read this again, and then I'll kind of catch you up to where I was. Now that the machine is calibrated, you're ready to begin molecule fabrication. Molecule fabrication always begins with just a single electron E and applying replacements one at a time, just like the ones during calibration. For example, suppose you have the following replacements. So this is the same, these 3 are the same, but then you have an E to H and an E to O. If you'd like to make HO, you start with E and then do the following replacement. E to O, O to HH, the last H to OH gives you HOH, right? So you can make HOH after 3 steps. Santa's favorite molecule, ho ho ho, can be made in 6 steps. And I kind of iterated through this, but you could imagine if you're at HOH, you now just have the H down here turn into a ho, and then you could have the O turn into a double H, and now this last H turn into a ho, or an O, and then a ho, to get 6 steps. But you can work through that and kind of see. The idea is, the way to think about it is you have a grammar. So if you've ever done, like, I think it was in the finite automata class, you create these grammars, and then you decide like what things can be made from these grammars. That's essentially what we're doing here. But the question it asks is, how long will it take to make the medicine? So given the available replacements and the medicine molecule in your puzzle, what are the fewest number of steps to go from E to the molecule? So the way to think about it is, you're going to start at E, and you need to pick one of these replacements. And then now you have a new molecule, this, and then you need to pick another replacement to get you there. And how many steps does it take for you to get to this giant one? And this is running right now, mostly to show you that I don't think that there's a easy way. You can't do this brute force. So that's what this is doing. Basically, I'm saying, hey, take all the replacements, try and do a replacement. So try and do a replacement, and then so perform that replacement, and now do a BFS search again of that new molecule and its replacements. So you basically are doing this over and over again. You're saying, oh, do a replacement, but you're doing it backwards, just to be clear. So what you're doing is you're saying, hey, look for, say I pick this one, look for CR CRNALAR. Look for this string, try and replace it with an H, and then call this recursively. And basically just keep doing that until you find the answer. And this has been running for, I don't know, an hour. Still hasn't found the solution. So that was just to kind of show that it's not going to work in that respect. You can't just do like this brute force, at least as far as I can tell. It's possible that I'm doing this wrong. I don't think I am, but it's possible. So where I left off was, that was not it. You can see here I searched for this AR. I noticed that I was trying to like bring these together. Like I want to match case as well. So you'll notice that in the replacements, AR is always at the end. And there's only there's no AR over here. And not only that, but there's no A and there's no R, right? So the way to think about that is, if you're working backwards, is that the only way you're going to get rid of this AR is if it's at the end of the string. And what that means is, I think, is you can definitely take this, you can assume that this is the only way this string is going to come back to E is if in total this fits one of these ARs right here, right? So at some point we have to get this AR to turn into one of these, right? And so part of me thought that maybe I can do like, maybe there's a limited way to go back. Like maybe there's only one way to go back in particular. Like, given there's only one way to have this string from these set of rules. Like normally when you have grammar rules, sometimes you get expansions that can expand infinitely. Like if we're going from left to right, how it's described right now, you notice this TI to TI, this TI to TI, right here. Part of the problem with this one is it can infinitely expand, right? So you almost wouldn't want to try all the cases starting at E and then working your way forward to this, because this one expands forever, right? It's circular is the way to think about it. However, it doesn't appear to be circular going the other way. That is, if you start with this, can we get to E? There's no circularity to it. So I think what that led me to believe was we probably need to find out, is there some way for us to like figure out what these are, right? And are there any other terminal things like AR? Like it would be nice to know if, like, for example, this string right here, there's only one way to get to this string. So we have CRNAR. So we kind of want to search for something along that. I don't know if we can do this in here, but if we do CRN dot star. Yeah, I can't do this here. I don't know how to do this here. But you'll notice these ones do start with CRN, and they all end with AR. So the question is, given this string, I have a CRN and I have an AR. Can this be translated down into into an AL or an FYFYF or an FYMG, right? So now, like, what I'm thinking is CASI. I don't see any CASIs. I see a lot of SIRN. SI. like right here. Ooh, and it, oh, okay, so here, this could be where it goes, is CACA can become a CA. So if I can get this into an R SIRN, BSIRN, BSIRN. BSIRN. Oh, B is a thing. Hmm. I guess I'm trying to find maybe the way to think about this is how many splits there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I guess I can. I only ever solve an AR at the end. So could I wonder if I could just try and solve this one as my input. And would it solve? Like the question is like how long does it just take to solve this one right here? Because if that one doesn't take long, maybe I can do it. So what I would instead of putting we'll say let molecule. Whoa, what happened? Are you seeing my screen frozen? Sorry, let me set this up again. Okay. So what I'm thinking is, what if I just try and solve that small piece? So we say let molecule equal this. Can I solve this small subset? How long does it take to solve? $28. So BFS fails. Ooh, am I doing something wrong then? Like that should return 0, right? Okay, that definitely works. That's this case. What is a simple case? CAP goes to P. No, wait. Let's go this way. H and F. So if I have OB and OB and CAF, right? That presumably should be why is that 0? Am I doing, is this wrong? Is 4 correct? So if I have OBCAF, I can go to H, which is 1, F, which is 2. Now I have HF 3. So this is actually not right. Okay, so maybe I'd have something wrong with my BFS. Presumably this should be, I can do OB, which is 1. Oh, I should have a min here. So I'm going to go through all the replacements. If I find one, I'm going to do the replacement and then try again. And replace... So I'm going to match on min and say if it's none. I'm going to do like this. Min equals... So I'm going to make this mutable. It's going to be sum I. Plus 1. Otherwise, if it's sum I, I'm going to say... Or sorry, J. I'm going to say... sum... min I plus 1. And I return min. Is that right? Oh, this is done. What doesn't it like here? The return type called due to argument pass. Try wrapping some... Oh, this is J. Hmm? Three, which is what I was expecting. So if I do this, I should get 0. Okay, now if I do this, what do I get? Hmm. Why would that not be the case? Oh, this could just be the left side of one of these. So like if I add this to it, maybe it then solves. No? Why doesn't that work? Maybe you can help explain it to me. Yeah, just to be clear, like this is one of those ones where I'm going to do a lot of like trial and error. Hmm. Why would the simple case work but not this one? CRNAR. It's clear that there's like these interesting rules, these CRNs, NRNs. Is there just a C over here? There is not just a C. There is an N, RN. How do I ever get rid of this C? It has to come from one of these, right? Or it could be this. Or these. N can turn into C, so technically this one could do it too. SI turn into CA, not CRN. Like what's going through my mind is something like this. The RNAR. Are there any other like that are like that? How do I it's like CRN and NRN. NRN is an interesting NRN clearly is like a no, it's not. This because this N can become one of these. This C, there is no C over here, right? There is a CA, but it only reduces to a CA if like this reduces to a CA. Is that what I need to look at? RNALR. RN FY FYFY. How many of the are there like that? FYF. CRN. Like, what's going through my mind is, what am I missing in this logic? I feel like there's definitely some part of the how do I say this? Like, this at the beginning of the string has to reduce down to something that is a part of an H, an N, or an O. So, like, it could be this CRN FYFAR, CRNAR, but it's, I mean, it could be this because this would reduce to an H. And then maybe the other parts of it give it to an F. Like, what I'm trying to go through my mind is like, there's an ORN, a CRN. There's a lot of these CRNs that I just don't know how you get. Like, what I'm inclined to think is, like, say it's this one, NAL. The only way you're going to get there is if you do like this one or this one, right? If it's NAL, I think the only one you can use is this. Maybe that's not right, though. But you definitely have to have this part of it boil down to something. Maybe the question is, is there ever an RN at the end? RNFAR. Ooh, right here. RNFAR. N. So can this boil down to an N? N. HSI. Yes, H. So can this boil down to an H? OB. So I can take off the B. So can this boil down to an O? There is no RN at the end. Is there? No. Is it just this one specifically? Maybe I try at the end. Let's keep trying to play around and see if I can't figure out. Like, can this one solve? Cassethan. No. Why is that? I am right, that the ARs are always at the end. Oh, but there could be another AR in the middle. What is that? What was that saying? RN. Oh, maybe it's not this whole string is one. CASI. CASI could be an SI. So now we're really just, we can turn this into this. SITH can be a CA. So CA. P, can this be reduced to a P? Ooh, maybe this itself may not ever reduce down to an E, but I can reduce this down to its smallest size. That's my problem. Is like this may not reduce to an E. That's why these are not working. These ones right here. It may not reduce to an E, but what it may reduce to is like an H or an F, which is like part of it. Okay, so trying pieces is not going to help then. Okay, that took me a long time. How long have I been at this now? Another 30 minutes. I'm at like 2 hours now, so. But that is to say, ooh, there's an AR. What does that even mean? Okay, before I get there, the path I was going down is, could I solve this part of it and then solve this part of it and then solve this part of it, bring them together, and then try and solve those parts of it. So like split by AR, reduce, merge, split by AR. But I think the answer to that is no. Or is it? Maybe, could I just write a reduce function that will reduce this to its smallest piece? And then go from do each of the chunks. This is a weird one though. There is no one that's just AR. So I think this is the one that breaks that logic, right? Because now you have an AR. Like what this is saying is there's some subset of an AR. There's some. How do I say this? AR is terminal, is like terminal in the sense that it's always at the end here, which means like this is this plus some part in front of it produces a terminal thing, but it produces a character that is terminal in this for this one. It's the second to last character of this one. Okay. Are there any other characters we know that are like ARs then? We know this R. Let's see. How do I say this? They all start with a capital letter, except for E. And there's no E anywhere in here, right? No, I don't see an E. So like this N is also terminal. This R is also terminal. and I'm probably using that incorrectly, but what it's saying is like R and N and A and R can't reduce further. So R and N and A and R must be in this part of it. So then how do you figure out this F can? Bummer. RNFAR. C also can't unless it's next to RNFARN. RNFAR can be an N. CRNFAR. Oh, is this the reduction of this? RNFAR. RNFAR. If there's an N, this becomes an O. So I need to find an N that fills this, and it's HSI. So the question is can this become an 8? Have I done this before? Can this become an H? It can if this can become an O. But that is not the case because I don't think anything ends in RN, right? Wow, I feel like this makes me feel like there's only one way to solve this. Like you'd only ever find one way. RN is not at the end. It's always the TITH. It's always the second. So we actually know from this. OMG. Are these molecules, by the way? Nitrogen, aluminum, hydrogen, fluoride, titanium, thorium, calcium, argon, erbidium. A Y? Where are the Y's? There are Y's in the puzzle. They're all in the middle. Most of them are these FYFs. FY, FY. What is F? Just a bunch of junk characters. CA. PRNFAR, PRNFAR. Yeah, like this is actually just a C. This is also another CA. Like, I wonder if it's these two. Are these interesting? Well, there's also this one, double TI. Are there any others that flow through? Or double and a half? But like what this is, like what's going through my mind is all of these CAs can be reduced to a single CA, especially if they have a PRN FAR or another one of these, right? Like part of me is inclined to look for CAs and TIs or see if I can turn them into CAs or TIs. And reduce this and get a count. Because it does make it smaller. The thing that's going through my mind is there's some of these that like go return to themselves, but a smaller version, right? So TI goes to TI, and KK goes to Ka. So two CAs go to that, but also all of these go potentially to that. And does that give me a better answer? SITH, I saw that one. Where was that? Sith. So that becomes, again, this becomes a chain of CIs, which themselves are just CAs, which themselves are just CAs. So do I find the chains and reduce them, make the molecule smaller, and then try and solve it from there? Are there any of those that are... So what I would be interested in is ones that, given themselves plus something else, reduce to themselves. So this is also one of them. If I find this, it's a simplification, right? This one is also a simplification. This one. This one. This one. Okay, it's gonna look ugly, but we may just try it for a second. Man, this one's... So we'll say let like dupes equal replacements dot iter dot map, no, filter on R where R dot 1 dot contains R dot 0 dot collect. So this should give me... What doesn't it like about that? Oh. that it? And so if I just I was thinking of just doing this recursively, but it could go deep, right? I mean, we'll try it. I guess I'm doing something similar to down here. If that's the case, I should probably just do it in a loop, right? So I should actually do this. I should say let cur equals molecule not to string, and then we say while just try and do a single replacement. Am I doing? I might be doing that for loop wrong. We'll think about it in a second. Gotta do it. You can do it like this and say so we just try and do all the replacements we can. Oh, but I'm only doing it for the dupes. See if I can get some smaller one. If they're the same, we break. Otherwise, we say cur equals next and next equals product clone. That. So I actually do need this on the outside to start. I just want to compare the two of them. So the first one is 469, the second one is 347. Although there's still like this SITH. Didn't I say that can become something? Oh, it can be a CA. So what has removed like this CA SIRN is gone. I just deleted it? That doesn't make sense. Oh, it's because the CASI, right? That would be it. There's a CASI that goes to SI. Yeah, right here. It seems that because of the order, it removes all the CAs. Is there something else about this then? I mean, this is a smaller molecule. So I could say do cur like this. Like I don't know if that it's definitely smaller, but it's not substantially smaller is the way to say about it. SITH. What is the SITH CA? If there's an RN, is there an AR after it? RNAR, 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 RNAR. Yes, 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 yes. Is that ever interesting? RNAR. RNARAL. AL is not. What were the letters that don't? There's AR and RN, F, B C A T I, yeah. B T R N F, yeah. Kaka P B B and P P R N A R S R F Y F. There's an F. Is it? There's no Y. Y, was that the other one? Y. Where are the Y's? Like, I'm trying to look for patterns. There are definitely fewer Y patterns. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Like, the thing that's going through my mind is, can I find like something that's really small in the list? Like, the fact that there's only 8 Y's. Like, when we did CA, there was like, it's like, I don't know, 60 of them, some number. There's a huge bunch of CAs, which means they're just going to keep reducing, right? To a bunch of times. But eventually something's got to reduce down to, like, what I'm thinking is like E goes to HF, but what H do you use and what F do you use? Like, it's possible that HF isn't the solution. Well, I guess it could be. There's definitely Y's in the, at least in mine, but there's only 8 of them, and there's not a lot of, like, what I was doing with the AR before. I wonder if we should be thinking about with the Y. Ooh. CRN, a bunch of Y's, ends in AR, NALCR, AL, ends in AR. I was wondering if we could find the exact one that this is, because that would technically reduce the search space by a third. Is this like a math thing that I just won't know the answer to? Like, there's some algebraic or mathematical formula? There's like a couple ways to think about this. Is obviously the brute force way is not working. I mean, I could have done my brute force wrong, but it feels like brute force is not working. So you want to kind of find something in the puzzle that says, oh, here's a hint at how you can reduce the search space. And so I felt like this ARs and the RNs kind of helped with that. Maybe I didn't go down the right paths to find those. But then the other way is there could just be a mathematical formula. that I just don't know. So what would that formula be? Like, given a context-free grammar, is there a formula to reduce to count the number of reductions to get to a value? That feels very... Because this could just be made up, right? It could be that it's not algorithmic, but it's like the part of the puzzle is, can you figure out the math problem in the puzzle? I've seen those before. Although they always related to something in the real world. Does it have to do with like biology or? Because these do look like they're things from the periodic table, right? Oxygen, potassium, silicon, thorium, titanium. I may not even be getting these right. B, I don't even know what that is. Is there a B? Boron. There is. Was I getting the other ones right? Yeah, titanium. Oh, P is phosphorus. What is potassium? PO? Nope, that's polonium. Oh, is potassium one of the weird ones that's not? Anyway, it doesn't matter. Ca, calcium, P, polonium, or phosphorus. Ti, titanium. I mean, it is periodic table stuff. Sorry, I'm looking at the other screen. Is there some kind of pattern to these? I think there is. Okay. Well, a small deduction. Let me just go through and make sure that's right. I think that is right. If it doesn't contain the RNAR thing, it always goes from like 2 to 1. Ooh. Oh. How does that help? I've been doing this so long I need to some chapstick on and take a drink. Like maybe the way to think about that is if there's just take this random string right here that doesn't have an RN or an AR. I can take that string and have it each time, right? So I can go from 2 to 1. And if I have a large group of them like this, there's 1, 2, 3, 4, 5. It takes um 1, 2, 3, 4. So n minus 1 to bring this down to 1. That is to say, well, I don't know how this is going to reduce, but because it doesn't contain an RN or an AR, it's always going to reduce 1 each iteration. So it's going to go from 5 to 4 to 3 to 2 to 1, and then it cannot be reduced anymore. And you can kind of do that recursively, right? If there's these two, I can reduce those 2 to 1, and these two, I can reduce those 2 to 1. And now I have CACASI. I can take the other two CAs and reduce it again. Now I have CASI. And then I do one more reduction to get to SI or whatever, right? So that is to say, I think in all the cases, so maybe I don't actually care about what's in between the the RNs and ARs. I just need to know how many of them there are. Not only that, but I actually don't care about CA M. Does M always follow a G? M does always follow a G. Ooh, there is TH and TI. That puts a part of me was saying, do I even care about the small letters? So how do the CRs see? They're not all RN. Yeah, let me just make sure that's right. I think that is right. They always go from 2 to 1. So we don't know what the 2 to 1. This is like a weird trick you can do. Like it happens in Sudoku puzzles. Like you don't necessarily need to know how it reduces, but you know that it can be reduced to some number. So you always know that like at each reduction, you're going to lose 1. So what does that mean? Ooh, I do think I can get the total number of molecules by just doing the capital letters, because the lowercase letters don't matter in that case. So like I can say, let's see, this stuff's not working, so we're gonna. We'll say this thing's been around the whole time, never solved it. What does it look like here? Oh. $274. So can I figure out what the count is minus the RNs and ARs? What was the other one? Y? Let me look at this again. F does. F MG does. F Y F. We know Y doesn't. F F MG F Y F MG Y F. Why are they all F M G? Oh, here's an AL. But we do have ALs. F or an F F or an F AR. So just Y's. So if I then like, how many RNs, ARs, and Ys are there? Are there other R's? Is there ever an R not by an N? No. But there is an AR, so I can't. Oh, I could do molecule dot matches, returns an iterator over the disjoint matches of a pattern with a given pattern. B. So I think I can do matches. Nope. Sorry, RN dot count. AR. Sorry, I'm trying to think through this. Like what's going through my mind is like there's 274 molecules. And if none of them were AR, RN, or Y, we could just say the count is 274 minus 1, right? That would be the solution. Because we know we could just reduce it once. So like let's do like a really dumb case. It's HF. We know, oh, we can just reduce HF to E. That's 1. So like you have 2 and it takes 1 reduction. And in a weirder case, we could do OB and SIAL, right? We know SI and AL can be reduced to an F, and OB can be reduced to an H, and then HF can be reduced to an E. Like those count down, right? There's 2 goes to 1, 2 goes to 1, and then those 2 go to 1. So it's always like n minus 1 that you reduce them. I hope I'm explaining that right. So if there were no AR, RNs, or Ys in the puzzle, the answer would just be 274 minus 1. Alas, there are... So maybe this doesn't help me? The AR and RN are like equal, which is interesting. And there's 8 Ys. I think I knew there were 8 Ys. I think I knew that too. Where there's an RN, there's always an AR, right? RN. Yeah. Where there is an RN, there's always an AR. Oh. So does RN and AR count twice? Is RN ever actually at the beginning? No. There's always something before it. Notably the C, which really annoys me. Like, it leads me to believe that this has to become an A. Right? Like, if this were in the path, this has to become an A. R and AR. But you would never get it to an A, a lowercase a especially. How do I reduce a C? Oh, I don't reduce it. It always has to be in this pattern. Oh, so like... it's actually not RN. It's CRN is in here. O reduces, though. N is reducible, presumably. Now I'm going back on thinking about counting them. Let's see, 274. 62. Is that the answer? It's either 203 or 195 if I'm thinking about this right. So like here's what's going through my mind. I know there's 274 unique characters, or what do I say this, unique molecules. Oh, they are molecules. We've been talking about molecules that I'm so daft sometimes. Daft. We know we go from we knew they were molecules because they said they were. Anyway, we know there's 274 distinct ones. And those will always just reduce down to 1. So if there were only those, it would be n minus 1, which is 273. And we know whenever we find an RN, it's paired up with an AR. So we have to reduce those. How do I say this? Those will be a reduction on their own, right? This set will be a reduction on their own. So we subtract those from it. How am I saying this? There's 2 of these, and normally that would count as 2, but it's only going to count as 1 this time. No, how do I say? There would normally be 3 reductions, right? So you'd have these 2, then you'd go to 1, and then to E. But you wouldn't. That's not the case because wherever there's an RN, there is an AR in the formula, so it's always going to reduce those down. I think that's right. Hold on, I may have to help someone. Okay, I'll get to this in a second. Oh man, I just lost someone asked me for some help, but I'm gonna try and finish this. Okay, sorry, I'm back. Hopefully that helped him. Okay. So where were we at? So 274 is the number of unique molecules. Whenever we find an AR or an RN, they'll reduce together. So we can subtract them from the count because when we found one, we would have found both of them, and so we can just subtract 62 from it. And then whenever we find a Y, that would have been in the AR. So again, I think we can subtract it twice, is like what I'm saying. I think this is, I'm going to take a guess and say it's this. Hot dog. Okay. So what is the, how do I solve this then? That's really weird. I actually don't, I almost want to look it up. So we know these things don't work. So it's molecule count minus Rn minus AR minus Y times 2 minus 1. Like, is that, I think that's what I said it was. I don't even need the replacements. That's actually hilarious. Yeah, because I'm not actually doing replacements. That's so weird. Okay, I bet you this one was a math one. And it, I've spent almost 3 hours on this one. So crazy. Like, I think what's happening here, again, so like what the intuition was, it took me forever to get there. I hate these math ones. I always do the worst on them. Like, if you analyze the problem, you can tell that if it's not an RNAR one, it's always going to go from 2 to 1, right? If you're going backwards, you're going to have 2 molecules and it's going to become 1 molecule. So you don't necessarily even need to know how these are converting. You just need to know that if it's a molecule, it's going to reduce by 1 each time. And so the way to think about that is it's n minus 1. So that's why you get the minus 1 here at the end. So it's the molecule count minus 1. Now the special case is if you have the RNAR, notice all these, they have a character, RN, something else inside, and then an AR, right? So what is that saying is if you have this, it's as if you're doing it, is as if you're reducing it at double the speed. That is to say, you can treat this as a reduction to this one. Sorry, you can treat this plus this as a reduction to this one. And so like you're like effectively doubling the speed. So you just need to know how many RNARs you have. And I actually just think it's times 2 is actually what it is. Maybe that's not the case. Maybe there's, I think that is. You can just say, oh, I'm just going to subtract those from it. But then you get the Y's. And like what my thinking was is the Y's are always in. I think we'd figured that out earlier. The Y's are always in. So we just need to, the Y's are the same way, right? But instead of meaning you've got some part on the left or right side of it and it reduces it in half. Maybe that's not correct. And did I just luck upon the answer? Let's go look and see. Okay, this might be it. No leaderboard today because I censor no. First insight. There are only two types of productions. E goes to XX, and X goes to XX. Yeah, so I think I figured this part out. And that production always goes to, so you go 2 to 1, 2 to 1, 2 to 1. That always happens. Or you get X, R, N, X, A, R, X, R, N, X, Y, X, A, R, X, R, N, X. Okay, so he's just he's saying remove everything but the RNs, Ys, and Rs. Yes, that was it, right? You can think of RN, YAR as the characters left paren, comma, right paren. So X goes to X parens that, X paren double the, whenever there are two adjacent elements in the molecule, you apply the first. Yes, this is the part, right? Whenever there's two adjacent, like, basic elements, you apply it. And then whenever you have one of these, you apply that reduces it by 3, 5, or 7. Ooh, so maybe I did luck into this. I needed to know that there were these 3 patterns, but like my thinking is like you find these pairs and then just that simplifies it. I may have lucked into it. We'll see. And whenever you have, yeah, so I think what he's saying is you, or they're saying is, you need to understand that, like, the basic, the non RNYAR molecules just reduce by 1 each time. And then the other ones are always of these 3 patterns. So maybe you're just looking for these 3 patterns. Let's find out. Repeatedly applying X to XX until you arrive at a single token takes count tokens minus 1. Yes, that's correct. A, B, C, D, E goes to blah, 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 and that's 5 times. Applying X to X0 similarly, except you get the things for free. Yes, this is what I'm talking about, right? Is the parens come with it, so you just, I was able to subtract the parens twice. So it's the total count minus 1, which you've already done, minus the count of this or this. Oh, so I did do, I think I did this part right? Like, this part is right, is I'm saying, look, if I have this or this, those ones are free, so I should remove them from the list, right? Like, that's the way to think about it. I wasn't doing it I didn't do it very well, but you can see it right here is these ones are free, so I can remove them from this list. I didn't explain that really well, but if you think about what I was talking about earlier, I think I said something to the effect of, like, these ones happen, it's like it has a net effect of doing it minus 1 here, minus 1 here. So, like, you subtract each of them that many times from it. And the gist is, like, this very reason is whatever one of these are, this and this and this and this come free in the reduction, so you can subtract it from them. So I think I did get that part right. Now you can generalize blah by noting that comma reduces the length by 2. Comma reduces the length by 2, comma x. New formula count is. That part I don't understand. This is the part where I may have lucked into. It was 2 times, but I think what I was thinking was there's some of them that it reduces 2, and some that it only reduces 1, so I just, like, doubled it. So this logic, so this part I think I did. There's been times before where I've, like, gotten it wrong, though, and not looked into it, so maybe I just got lucky. But what they're saying here is 2 times count. The way to think about each comma is the comma is getting reduced for free in the X. So regardless if it's a 2 commas or 1 comma, like this inner reduction, you have to reduce this in, and then you get the comma for free. This reduction, you do this, and you get these 2 for free. So this is a reduction of 3. This is a reduction of 2. So 3 characters to 2, 5 characters to 3, meaning it's 2 times Y, which is this. Oh, here's Topaz. He's the person that makes them. This is the correct answer. In fact, internally, RYAR exactly map to block comma. Duh. Okay, so when he wrote the code, he actually intended it to be these. Actually, there's even more of a pattern, but if you've gotten this far, I'll wait to explain the rest in case someone wants to try to figure out it on their own. Hint. It is based on chemistry, but not the atoms you're seeing. You have enough of the pieces here to deduce why the puzzle isn't just guess random and win. This is actually the production rules for an unambiguous grammar, at least unambiguous in terms of step count, which is all that matters. That's crazy. Okay, so I do think I got to this. Are there ways other people solved it? Alpha goes to beta, gamma goes to beta, RN. Okay, so I think he found a similar solution. This looks a little similar. Well, this guy got first place. BFS didn't work. Yeah. I mean, I don't presume it would have. Okay. So where do we go from here? I mean, this was a hard problem. If you're still actually here, congratulations. And again, I'm at like an hour and a half or an hour and 45 minutes of recording. I had gone an hour before. So I think these videos where I do them live, some of them are just going to be like mega long. If I'm not familiar with like, oh, I can use this algorithm and it's just me remembering the algorithm, those things probably take an hour or less. But here, looking at these solutions, it does look like I eventually came to the right one, which is to say, you need to find these patterns. And if you do, you don't actually even care about how to do it, but that you can count to do it. I think this is an interesting, I would like to search more about this and see. I'm also curious how someone like ChatGPT might solve this. So I may do that. Can you solve the following puzzle with using Rust? The input looks like this. Sorry, I'll pop it over here, see what it says. Part 1. We want the shortest number of steps from E. However, generating E upwards is explosive. Reverse all rules. Try to reduce the final molecule to E using greedy. This works surprisingly well. Does it? You can use... I thought I had tried greedy. Maybe it was in the first hour and a half that I lost. Reduce to E. Replacements, iter map. So you're switching them. Sort by. Does this actually work on my thing? Why does it need regex? Looks like it's parsing the input using regex. Is that right? I'm going to take this. Molecules. Placement string. I don't know why it does this. Okay, I'm inclined to try this even though... Oh, I need to deref these. And then molecule replacements. Why doesn't it still like that? Oh, that. Panic. No replacement found. Stuck. Yeah, I don't think this works on all solutions. Like what this is saying I can do is, oh, if I just use a greedy algorithm to solve it, it doesn't work. Maybe it works on some of the inputs, but it doesn't work on mine. That's possible. Yeah, there are a lot of people that say a greedy algorithm works, but it doesn't on mine. Okay, this person says you randomly shuffle. Okay, so maybe that works. Let's try that really quick. So we can say if not replace, we just return none. Oops. Otherwise, we return some steps. How do I shuffle an array? Shuffle a vec. Okay, I mean, I can do this. So like basically what I'm doing is I'm randomly picking a new thread. Oh, it still doesn't feel like it's finding it. Like essentially what this is saying is, oh, I'm gonna go try a bunch of I'm going to try and do replacements in a specific order until I find one that solves it efficiently, but that doesn't feel like it's any better than brute force. And so I mean, I could have done this wrong, but it doesn't feel like it works. So, you know, it's possible that for at least for my input, the math way was the only way. Oops. Yeah. Okay. I mean, I tried a couple ways, and I actually don't think there is another way, at least for my input. It's possible that some other inputs may have resolved faster. And this can happen sometimes. I've had them before where, like, I say to myself, oh, maybe the brute force solution just works because of the way that it's designed, and it solves it in like 2 seconds or whatever. And you're like, okay, well, I got to the answer. Was that magic? But that solution doesn't work for other people. And it seems like now I'm on the other side of the boat where it's like people are saying, oh, if I just try these random things, of course, I did try and do it in my own. So maybe I'm doing it wrong. Maybe I can find someone's greedy solution. Got me 13 points. Not convinced, but looking at my input, it works. So here's a go solution. We could see if it finds it. How does his work? What do I need to do? I just pass it to standard in. Get stuck. Is it just printing this a million times? Yeah. It gets stuck. So that one doesn't work. I don't have Haskell installed. I don't know. Maybe up at the top. This is the answer I came up with in the long run. Over near CYK. I don't understand how CYK. It's just a parser. Like it's just supposed to say, "Can you do it?" Maybe it's updated to count. I don't know. I would like to find a solution where I do actually just solve it. Python 2, part 2 in Python with randomness runs hilariously quick. I would need to know how to do this, and I haven't done Python in a while. In Python, how can I split a string? INN. Okay. Can you write a function to return the two parts reading from standard in? Can you update it so that part 0 is split again and each split again by -n, and each line is split by this. This is a lot of work to get to this. So like that. So if I do this, but then I do python main.py. Oh, is this in? Is this still gonna work because it's in Python 2? Sys. It worked. What the heck? It worked really fast too. Okay. Maybe I was doing the other Rust way wrong. What is this doing? It's saying, okay, find, I have a target. Set my temp to the target. For all the replacements, if I don't find the from line, skip it. Otherwise, do the replace and increment. And you just do that. And you keep doing it. And if you ever go through this for loop and don't change, that's what this is saying, then start over and shuffle the reps. I must have been doing it wrong in Rust. Okay. I mean, that does solve. That's crazy. Okay. Okay, I've talked about this way too long. We're already at a 2-hour video. If you're still here, thank you for watching. Hopefully day 20 won't be as long. Can't make any promises though. I hope you had fun though, learning and learning along with me. Let me know how you solved it though. I would love to see your solution. Even if you solved it 10 years ago. I've solved this before. I don't know how I solved it before. I don't remember. That's why day 2015 I solved several years ago, so I don't remember how I solved it originally. I guess I could go back and look. But anyway, however you solved it, I would love to see. If you did something like this in Python, that would be cool to see. Otherwise, yeah, we'll see you next time for day 20. Bye, everybody.